John Black, super chemist. We're here to make some potassium sodium 2,3-dihydroxybutanedioate. A lot of people call that Rochelle salt. What do I got here? I got 47 grams of cream of tartar, and I got 13.25 grams of sodium carbonate. I have a little bit over 100 milliliters of boiled that water in there and make sure that it stays hot. And I'm going to add this cream of tartar. As you can see, it's not very soluble. That's why I have to have the water heated up. Hardly be anything that'll dissolve. Just like when you put baking soda and vinegar, this is going to make some carbon dioxide and it'll bubble. So you just want to add a little bit at a time. I'm going to put a little spoonful. You can see the effervescence. I got most of the sodium carbonate in there. I just dumped a bunch in. It didn't really bubble a lot there. So it must be close to being done to reacting, because otherwise it would bubble a lot more than that. So I'm going to stir this up for a little bit. As you can see, everything's dissolved. It did turn it brown, which I don't like. So I'm going to filter it. So that's what I got. It's a dirty colored water. After a day, this solidified. I had it on a heating source, and it got too hard. I mean, it was hard as heck. So I put some more water in it, and this is like a day after that. It's somewhat hard, but I can break it apart, so I'm going to filter it. I'm going to pour some ice cold water in there. Well, there it is. I'm going to see if I can also recrystallize some of the rest of that liquor. Now I seem to have the same problem. It either gelled up or it turned into a complete solid, and I couldn't wash out the crystals. So I'm going to filter it. And there you go, second batch. Alright, I'm going to do this experiment a second time, this time with no heat. Alright, I got 100 milliliter of just regular water, room temperature. I'll have 47 grams of the cream of tartar. When I add the sodium carbonate when it's cold, it doesn't fizz really. I mean, it does a little bit, but not like it did when it was hot, that's for sure. I let it stir for a little bit, and it's not very soluble, so I'm going to add a little bit more water and let it stir some more. It's still bubbling. It's been 2 hours total that's been stirring. As you can see, there's precip down at the bottom there, just like a layer. Compared to what I put in, it's nothing, though. So, screw it. I'm just going to filter it. I'm putting it in a shallow, bigger pan than the other one because I'm not going to use any heat, and so this is going to take forever to evaporate totally naturally. So I give it more surface area this way. Well, there you can see it's crystal clear water. You can see that film on there. Yeah, it's white. So that's what didn't react. Here's after about 2 or 3 days, I put it in a bigger pan so it'd be nice and shallow. You can see lots better, looks better than crystals, but I'm gonna filter this and wash it up with some cold water. Well, there you go. I got 29 grams of nice clean crystals after one crystallization. There's my theoretical yield. There's what I got from the heating one. There's one from no heating. You can see I only got 57% from the heat one because I couldn't really put it in the refrigerator or cool it down too much because it would gel and you can't clean it. It's like jello. I got 82% though of the stuff that I used no heat, and it only took about 3 days for it to, evaporate. I put it in a real shallow pan, so it was no big deal really. But I want you to see what the crystals look like. The one on the left I did slow with no heat. They both need recrystallized, but the point is I got more with the no heat, and the crystals look great. Before I go over my stoichiometry, I want you to remember a previous video called How to Make Sodium Ethanoate. Most people call it sodium acetate. We took acetic acid and we put in some sodium bicarbonate and we made sodium acetate plus carbonic acid. Now, maybe in the video I didn't bring up carbonic acid, but that's actually what you make. But carbonic acid breaks down into H2O and CO2. Okay, so probably in the video I just said this formula, but it's the same thing because this breaks down real easy. So what we could have done was we could have used some sodium carbonate. That's what we made in the last video, how to make sodium carbonate. Basically, we just heated this up. We drove off a water molecule and a carbon dioxide molecule, and we ended up with this. Now look at this formula. You could take that sodium carbonate, and now there's 2 sodiums, right? You could take 2 of these acids and make your sodium acetate salt and get another water and a CO2. So they basically do the same thing. Do you see how the formula is pretty much exactly the same, except for this one has 2 sodium ions, so it has 2 acid ions. That's the only difference, and it makes 2 sodium salts. Other than that, they do the same, accomplish the same thing. Now I want you to keep in mind, no matter what is on the end of this molecule, as long as it doesn't react with sodium bicarbonate, this can be as long as you want. Look at this acid now. See how it has more carbons? You go through the same reaction and you just make this. See how they're the same? The same reaction, same thing. Doesn't matter what's on this, as long as it doesn't react with sodium bicarbonate, it'll just do the same reaction. And whatever you have extra over here, you're going to put extra over here, right? Same with the sodium carbonate. Does the same thing. Now remember, this is what we made before. We had acetic acid. I have potassium here, but sodium and potassium are interchangeable pretty much. So if you put potassium carbonate or potassium bicarbonate in with this, you would end up with potassium acetate. Notice the ending, IC8. Now we're just doing the same thing. See, the black part shows you that this is exactly like this. And this is called tartaric acid. See, ick. And when I put some potassium or sodium carbonate or bicarbonate in there, it will take the first, as you can see, there's two sides here where it actually has a carboxylic acid. So it will make the potassium bitartrate, and bi because it's only done one side, and that's why they say that. This is actually the cream of tartar that we bought. Okay, this is the cream of tartar. Now I want you to look over here because there are two. If I flip this around, that's what I did over here. See how the potassium is on this side? I basically picked this up and went like that. Okay, so that this side is now on this side. See how you have another? It's just the same exact thing as acetic acid. So basically this side's already done when we buy it as cream of tartar, right? So all we have to do is get the other side to make that salt. And that's the part we're doing. And that's called potassium sodium tartrate. Just like over here, we replaced the bi with sodium. And the reason why I called it potassium sodium 2,3 dihydroxybutanedioate is because that's the IUPAC name for it. And obviously potassium sodium, you get that. 2, 3, because you number these carbons, 1, 2, 3, 4. And the hydroxyls or hydroxy groups are 2 and 3. So 2, 3, and there's two of them, dihydroxy. When you do carbons like alkanes, you count 1, 2, 3, 4. That'd be butane. And then there's two di-OAtes. Eights means there's a salt. There's two salts, a sodium one and a potassium one. And that's the IUPAC name for it. Most people just call it Rochelle salt. I hope I'm pronouncing that right. So look at this new equation. This is what we had, cream of tartar, right? Instead of acetic acid. We use sodium carbonate. Sodium carbonate is in this formula, but we've seen how sodium bicarbonate does pretty much the same exact thing. And when you get on the other side of the equation, carbon dioxide, water, both places. And you also get the sodium, see how it's positive, salt of the acid. That's it. I want you to see something. Look at that. Doesn't that look exactly the same? Boom. Look over here. Look at that. Doesn't that look like the same molecules up on top there? See this and this? It's the same exact equation. It's the same exact thing. Because all this other stuff does not react. You already have a salt on this side, so it's going to stay the same. How did I figure out my stoichiometry? Here's the formula. It's two of these. One of these makes two of our product, right? This is cream of tartar, sodium carbonate. Here's the molar mass of this. Now we need two of it, right? So I multiplied it by 2. Now I'm only going to use an eighth. I'm multiplying everything by an eighth. So I divide by 8, and I get 47 grams. That's how much I used in the experiment. What about the sodium carbonate? The sodium carbonate. It's 106 grams per mole. I divide it by 8 because I only did an eighth of what I was supposed to here. And I get 13.25 grams, and that's what I put in. Now my estimated yield, okay, it's going to be 218 grams per mole, but this is a tetrahydrate, and we're going to crystallize it out of water. So that means there's going to be 4 molecules in a tetrahydrate. So that's 282 grams per mole. So up here, we divide that by 8. Our estimated yield is 35.25, our theoretical yield. But we're going to have to crystallize it and maybe recrystallize it a second time. So we're going to lose some product there. Anyways, I always remember, science is great.